Hi everyone, welcome to today's session. This is Dr. Mahender, Associate Professor of Mathematics, B.V. Raj Institute of Technology, Narsapur. The course name is Linear Algebra and Calculus. The topic name is the quadratic form. So before going to today's class, just quickly I will recap the previous session. So mainly we diagonalized the non-symmetric matrix in the last session, but I did not diagonalize the symmetric matrix because that concept is I'm going to cover in this session. Now this topic is the quadratic form. The quadratic form is a plays very important role in the principal component analysis, and that is the principal axis theorem. So let us start with the definition. What is meant by quadratic form? A quadratic form is a homogeneous polynomial of degree 2 in n variable is called a quadratic form. So in general we can represent the quadratic form in n variable by a11 x1 square, a12 x1 x2, and so on, an and xn square. So what is the definition of the quadratic form? Quadratic form: a homogeneous polynomial of second degree in n variables is called quadratic form. So short form writing QF. So any homogeneous polynomial of second degree. So any homogeneous expression of second degree in n variables is called quadratic form. So what is the most general representation of the quadratic form? The most general form of the quadratic form is the most general form of quadratic form is generally we represent the quadratic form by this capital Q. So we'll write a11 x1 square, then a12 x1 x2, and so on, a1n x1 xn, then plus a21 x2 x1, a22 x2 square, plus so on, a2n x2 xn, similarly and so on. This is an1 xn x1, and so on, an2, then xn x2, and so on. This is ann xn square. Now look at this expression. If you look at the degree of any term, you look at it, even if you take the first one, what is the degree of this? The first term we have the 2. Even if you take the second term, what is the degree of this one? So this 1 plus 1 is 2. So now look at this total entire expression. Each term have the same degree, that is 2. Therefore, it is a quadratic form in n variable. So, or this we can represent in the short form also. Yeah, we can represent by this Q is equal to summation I going to 1 to n, summation j takes from 1 to n, a ij xi xj, where a ij are real numbers. Here, whatever the coefficient we have considered, you have taken as a real number, so that this quadratic form is called real quadratic form. Now we can how we'll get this expression by this summation notation. Just plug in I is equal to 1 and j is equal to 1. What happened? Look at this one, a11 x1 x1 is x1 square. Again, I is equal to 1, j is equal to 2. If you substitute, we'll get this one. In the same way, by keep on changing the I and j values, we'll get the entire expression. Therefore, it is a quadratic form in n variable. Let us will give one example for the quadratic form in 2 variable and 3 variable. For example, x1 square minus 6x1 x2 plus 2x2 square is a quadratic form in 2 variables. Why it is a quadratic form? It is an expression. How many variables are involving? 2 variables are involving. Then how we can say it is a quadratic form? You look at the degree of each and every term. If the degree of each and every term having 2, therefore we can say that expression is quadratic form. Now look at that, verify. Now look at this. What is the degree 2? What is the degree of this one? 2. What is the degree of this one? 2. Therefore, it is a homogeneous polynomial of degree 2 in 2 variables, namely x1 and x2. Suppose if I, for example, x1 square minus 2x1 x2, for example, x2. Is it a quadratic form? No. It is not a quadratic form. It is not a quadratic form. Why it is not a quadratic form? Now look at the degree of this each and every term should be homogeneous and equal to the 2 only. Coming to here degree 2 we have. Here degree, this 1 plus 1 is also 2. But coming to this one, the degree 1. So it is not a quadratic form. It is not a quadratic form. So quadratic form must be a homogeneous polynomial of degree 2. Then otherwise it is even if you fails in one term, it is not a quadratic form. Let us try to, we'll give one more example, quadratic form in 3 variable. x1 square, 2x2 square, 3x3 square, minus 2x1 x2, 4x2 x3, minus x3 x1, minus x3 x1. Now it is a quadratic form. Is a quadratic form. Is a quadratic form in 3 variables. 3 variables. Why it is a quadratic form? If you look at the degree of each term having 2. So how many variables are involving? 3 variables are involving. Therefore, third one is a quadratic form in 3 variables. And particularly this quadratic, all these quadratic form are real quadratic form. Why we are calling real quadratic form? If the coefficients are real numbers, that quadratic form is real quadratic form. If the coefficients are complex numbers, we can call it as a complex quadratic form. But we are dealing with only real quadratic form, so that I have taken the real numbers. Whatever the problems we have are associated with the real quadratic form. Okay. So next, so we have one important theorem regarding this quadratic form. Every quadratic form we can express in the matrix form. Then how that theorem is? Every quadratic form in n variables say x1, x2, xn can be expressed in the form of x transpose ax. So every quadratic form in n variable we can express in the matrix form. This is a matrix form x transpose ax, where here x is the column matrix of, that is x1, x2, xn, and compulsory, and A is symmetric matrix. A is symmetric matrix. So whenever if you express the quadratic form into matrix form, the whatever the matrix will get, definitely will get the symmetric matrix. Okay. So here A is what? Symmetric. What is the symmetric? A transpose is equal to A. A transpose is equal to A. Or we can say, by this theorem, we conclude quadratic form if and only if there exists a symmetric matrix. For every symmetric matrix, we can convert into quadratic form. Every quadratic form, there exists a corresponding symmetric matrix. Now we will do, we can express one quadratic form to how to express the quadratic form to matrix form. Or every symmetric matrix also we can write it as a quadratic form. So we will take first proper example. Example 1. So Q is equal to x1 square minus 4x1 x2 plus then 3 x2 square. Is it quadratic form? Yes. Why? Because it is the expression in two variable and each and every term having degree 2. Therefore, it is a quadratic form in two variable. Is a quadratic form in two variables, x1 and x2. So according to this theorem, every quadratic form we can express in the matrix form. What is the matrix form? That one? The matrix form is this one, x transpose x. So therefore, according to above theorem, we can write it as x transpose ax. X transpose ax. What is the x he has mentioned? X is compulsory the column matrix. So this column matrix, then how to take the column matrix? Whenever x is the column matrix, the x transpose will become row. So x transpose will become row. Now suppose if the given quadratic form is 2 by 2 in two variable, we'll get 2 by 2 matrix. The matrix of here, this is the matrix, you write it in the way. Then how to write the order? If the quadratic form in two variable, the matrix will get the 2 by 2 square matrix. Suppose if quadratic form is three variable, we'll have to write it 3 by 3. You have to write it. Okay. What is the x here? X is the column matrix. X is the column matrix. What is that one? x1, x2. According to this theorem, what is the x here? X is the column matrix. What will become the transpose? Will become transpose will become row x1, x2. Now the order will become 1 by 2. So this is the way of writing the quadratic form to the matrix form. So first what we have to do is write this type of matrices boxes. Then first you have to write the right hand side x, then the left hand side x transpose, you write it. After that you have to fill the coefficients, write the matrix. How to write the matrix? First write the diagonal elements. The diagonal elements are nothing but the coefficients of the squares. For example, now look at here. This is the matrix. This, let us say this is x1, this is x2. Here this is x1 and x2. If you multiply, what will get here? x1 square will get. Here what will get? x1, x2 will get. Here x2, x1 will get. What will get? x2 square. Just to look at this diagonals. Diagonals are nothing but the coefficients of squares we are writing. So what we have the coefficient of x1 square? Write it as a1, 1. What is the coefficient of x2 square we have? This we have to do is the first step. What we have to do the first step? First you write the diagonal element by observing the coefficients of the squares. Okay. After that you have to fill the non-diagonal element. Then how to write the non-diagonal element? Now look at the non-diagonal elements. Here x1, x2 is the non-diagonal element. Whatever the coefficient we have here x1, x2, by 2 we can make it. What we have here? Minus 4. By 2 we can do it. Make it half. Whatever you get, that you have to write it in x1 and x2 place you are writing. So therefore what you write? Minus 2, minus 2, minus 2, minus 2. So even if you multiply also, if you multiply this one, we'll get the given quadratic form. Then how it will look at this one? Suppose if you multiply, what you will get? If you multiply this 2, if you multiply, this is the 2 by 2 and 2 by 1, will get the 2 by 1. Okay. Now here what we have here from this 1 by 2. Now this, if you multiply this 2, what will get? 1 by 1. So 1 by 1 nothing but is the quadratic form. Even if you multiply also, you will get the same quadratic form. So therefore, this is the way of writing quadratic form to matrix form. And look at this here. What is the A here? A is equal to what? 1 minus 2 minus 2, 3. So definitely we'll get the symmetric matrix. So whenever if you express the given quadratic form to matrix form, whatever the matrix you will get, compulsory you will get the symmetric matrix. So even if you suppose you won't get the symmetric mean, you understand that you did somewhere mistake there. Okay. So look at what how to verify the symmetric. The first row is identical with the first column. The second row is identical with the second column. So that we can write it as A transpose is equal to A. A transpose is equal to A. So from this note also we can look at the notes. Every quadratic form we can write in the matrix form. So the matrix, whatever the matrix will get in that is symmetric matrix. For every symmetric matrix you can express in the quadratic form also. Now we will take the matrix. Then how to write it in the quadratic form, every symmetric matrix. We will look into this one. The first one we have to express the quadratic form to matrix. Then suppose if you have the symmetric matrix, then how to write the corresponding quadratic form. So example 2. Write quadratic form of the following the matrix. What are the matrix? We have 1 minus 2 minus 2, 3. So compulsory for every, is it symmetric or not? Yes, it is symmetric. For every symmetric matrix, we have to write the corresponding quadratic form. Then how to write it that one? Very simple. Very simple. Suppose we have the matrix this one. This is the A. 1 minus 2 minus 2 and 3. Here you will take it as x1. This is x2. This is x1 and x2. So the way of writing is quadratic form is from the symmetric matrix is first you have to write the square as the diagonal coefficients. What are the diagonal elements we have? This one. So this write the x1 square and 3 x2 square. So whatever we have, this is over this. The coefficients of the squares are the nothing but the diagonal elements. So whatever we have here, these non-symmetric elements. These are symmetric places. This is what symmetric places we write it. What is mean by symmetric places? Symmetric matrix means x12 is same as x2. So whatever we have this one, we can add it and write it. Whatever we have x1, x2 here, minus 2. Here x2, x1 is what? These are the called symmetric places. Okay. So we can write it as minus 2, minus 4, x1, x2. Minus 4, x1, x2. So first how to write it? For example, if I take one more example, look at this one. So I will take one more symmetric matrix. 1, 2, 3, 2, 3. Now this is the 4, 5, 5, 6. Is it symmetric? Yes, because A transpose is equal to A. First row is identical with the first column, the second row is identical with the second column, third row is identical with the third column. Then how to write the quadratic form? And quadratic form will get the, in 3 variable will get it. Because of A is 3 by 3 matrix, we'll get the 3 variable. So how to write it that one? Let us take, this is the x1, this is x2, this is x3. Here, this is x1, x2, x3. x1, x2, x3. So better I will write it as this one, like this is q is equal to, what you are trying first? Squares you are trying. What are the squares? The squares are the The coefficients of these scales are the diagonal elements. What are the diagonal? What is the x1 square will get? 1 x1 square. This is what? 4 x2 square. Then 6 x3 square. First, what you are writing? Coefficients of the scale terms you are writing. Then how you will get the coefficient from the diagonal element you are writing? The coefficients of the scales are the diagonal. Then look at these are the symmetric elements. This is x12, this is x21. Suppose look at this one. I will make it clear. This is x1, x2, x3. This is x1, x2, x3. This is what we will get x1 square. This is x1, x2. Multiply this is x1, x3. In the same way, this is x2, x1. This is x2 square. Then x2, x3. This in the same way x3, x1. Then x3, x2, then x3 square. Now look at this one. So the coefficients of the scales lies on the word diagonal. So in the same way, so while writing this first scales, you write the coefficients are the diagonal elements. Okay. So x1 coefficient is what? This one. So after that, whatever we have, look at this one. These two are nothing but same. These are called symmetric places. Let us say this is x12 and x21. What are the x12 we have here? x12 and x21. 2 plus 2. Add and write it. This is right. 4 x1 x2. Now this is over. Okay. So while writing from matrix to quadratic form, you can sum up and write the coefficient of that one. Coming to this one. What is this one? This is x13. This is x31. What we have? 3 plus 3? 6. 6 x1 x3. The next one, other symmetric place is what? x2 x3. What we have? x2 x3? Here 5, here 5. Plus 10. 10 x2 x3. So this is a way of writing from the symmetric matrix to quadratic form and quadratic form to symmetric. Suppose if writing quadratic form to symmetric, for example, if we have this one, how to write the matrix form this one? How to express this matrix form? For that, what you have to write? Q is equal to x transpose AX. X transpose is what? The row. Here we'll get the 3 by 3 matrix because it's the 3 variable. Here you have to write the x. What is the x here? x1, x2, x3. What is the transpose? x1, x2, x3. So from this, how to fill this A? How to get the A? Very simple. Now look at this one here. x1 square, x2 square, x3 square. Write the coefficient you are writing. What are the coefficients of x1 square here? We have 1. What is the coefficient of x2 square? 4. What are the coefficients of x3 square? 6. Then you have to write this position x1, x2. Whatever we have this one coefficient of x1, x2, 4. Then while writing this matrix form, you have to make it by 2 and distribute here x12 and x21. So that what you have to write this is, or we can say by 2 you make it. You can make it as a by 2. So half of the x1, x2, x1, x2. What is that one? 2. Then what are the x1, x3 we have? 6. Again make it by 2. Make it half. 6 by 2 is the 3. We'll write here and here. Then what is the x2, x3? 10 we have. Again by 2 you can make it. 10 by 2 is the 5. Then write it. So if you multiply, this is the 3 by 1. This is the 3 by 3. This is the 1 by 3. If you multiply all these, the result will get 1 by 1. That is nothing but this you will get. So that from this, what you have to conclude, every quadratic form we can express in the matrix form. So whenever you express in the matrix form, the matrix is always you will get the symmetric matrix. And vice versa, every symmetric matrix also we can represent in the quadratic form. There exists a corresponding quadratic form. Okay. So now we will move to the transformation of the quadratic form. What is meant by the transformation of the quadratic form? transformation of quadratic form. Transformation of the quadratic form. Let x transpose ax let q is equal to, I'm taking the matrix form, x transpose ax be a quadratic form in n variables, say x1, x2 and xn. Now I'm taking one relation here. Let x is equal to py be a linear transformation. Which transforms variables x1, x2 and so on, xn2, the new variables y1, y2, yn. Now what is the y here? Y is the column vector where the y is, what is the column vector? y1, y2, yn. So now what I am doing here, the given quadratic form is what? Q is equal to x transpose ax. Under this transformation, x is equal to py and x is equal to py, it is transformed to the quadratic form in n variable to the new variable. How it will be changes? Just look into that. Let x transpose the given now. What is the given quadratic form? X transpose ax. So in that substitute in place of x py whole transpose a py. Here, what is the, let x is equal to py. X is equal to py. We know what is the dimension of this x? This is n by 1. This is P is one square matrix of order n by n will get. This is n by 1. If n by n will get, again n by 1 will get. Okay. Now we know in the matrices the AB whole transpose is equal to what? B transpose A transpose. So Y transpose, the P transpose AP 1. Because here whatever the matrix we have, it is symmetric matrix. And we know that every symmetric matrix is diagonalizable. Every symmetric matrix is diagonalizable. Means there exists a P inverse such that P inverse AP is equal to D. But here in the process of diagonalization, whatever the model matrix will get is orthogonal. So whenever if the matrix is orthogonal, the P inverse will become P transpose. Now we will see in the problem this one, in the concept of diagonalization of the symmetric matrix. So P transpose AB is equal to what? D. D is what? Diagonalization, diagonal matrix, and diagonals are the eigenvalues. Y transpose D1. Y transpose D1. What is the Y transpose? We know Y transpose. Y1, Y2 and Yn. What is the D? D is the diagonal matrix. Suppose if lambda 1, lambda 2 and lambda n are eigenvalues, then we'll get this one. 0, 0, lambda 2, 0, then 0, 0, lambda n. This is y1, y2, yn. If you multiply this 3, this is what is the n by 1. it is a new variable. This is the n by n. This is the 1 by n. We'll get 1 by 1. We'll get lambda 1 by 1 square, lambda 2 by 2 square, and so on, lambda n by n square. Now, this is also quadratic form. But look at the given quadratic form is what is in variable n variable. It is in x1, x2, xn. So under this transformation, x is equal to py, this x transpose ay will become y transpose dy. Now y transpose dy is in quadratic form, but if you look at that one, it is a special type of quadratic form. In that the product terms are absent. Only the sum of scales we have. This type of expression is called particularly canonical form, which is known as a canonical form. Short form writing CF. So I am reducing the quadratic form to canonical form, one of the linear transformation. What is the linear transformation? X is equal to py. So the canonical form also quadratic form, but in that expression we have the product terms are option. Only the sum of scales, the expression which is having sum of scales, that type of expression is called canonical form. So this we have the applications in the principal axis theorem and principal component analysis. It is one of the dimensional reduction techniques. But here in the syllabus we have the reduce the quadratic form to canonical form by using orthogonal transformation. This is the major concept we have that one. So that will cover in the next class. But now what is the procedure for that one? And generally the question will ask reduce the quadratic form to canonical form by using orthogonal transformation. After reducing the canonical form, from the canonical form find what is the rank, then index, signature, nature. Once you reduce the canonical form, by observing the canonical form, we can find the rank also. These three terms we will write it. What is the rank? Then rank we can write the small r. Then index, then Smith, and signature. Yes. And if you look at carefully, the coefficients of this y1 square and y2 square and yn square, nothing but the eigenvalues. So even if you get eigenvalues also, we can easily get the canonical form. For example, suppose if A is the 3 by 3 matrix, A is the symmetric and 3 by 3 matrix, and A is the real symmetric matrix of order 3 by 3. Therefore, it is diagonalizable. If you diagonalizable, for example, if eigenvalues are, let us say, 2, 3, 6. So finally, the quadratic form X transpose AX, the quadratic form, suppose we have the quadratic form X transpose AX, X transpose X. If you reduce to this canonical form by using orthogonal transpose, this will become y transpose dy. And this easily we can get that 2y1 square, 3y2 square, 6y3 square. So compulsory the coefficients, what will get the coefficient? The coefficients will get the eigenvalues. So once you know the eigenvalues also, we can guess that the right is the canonical form. The canonical form is what? The only squares, the coefficients are the squares are the eigenvalues. If suppose the eigenvalues are 2, 3, 6, so finally what will get the canonical form? 2y1 square will get 3y2 square, 6y6 square. It is called canonical form because having only square term, product terms are absent. Such expression is called canonical form. So after reducing the canonical form, we can find these things. One is the rank, the index, and signature. Very simple. Rank is the number of terms in the canonical form is called rank. Number of terms means nothing but number of eigenvalues. Look at, for example, this one. How many terms we have in the eigenvalues? 3. Therefore rank 3. What is the index? Number of positive terms in the canonical form. That is associated with the eigenvalues. Nothing but number of positive eigenvalues. How many eigenvalues? 3. 3. Then signature. The positive number of positive eigenvalues minus number of negative eigenvalues. Positive eigenvalues 3, negative eigenvalues 0, therefore 3. So, what is the rank? The number of positive terms in the canonical form is called rank. Then the index, the number of positive terms in the canonical form is called index. What is the signature? The number of positive terms minus number of negative terms is called signature. After that, we can write the nature of the quadratic form also. Nature of the quadratic form. After reducing, generally they will ask this 3 and along with they ask the nature also. What is the nature of the quadratic form? This is using with eigenvalues also we can tell that. So nothing but the canonical form is depending on the eigenvalues. From that eigenvalues we can easily conclude the nature of the quadratic form. If all eigenvalues are positive, we can say positive definite. If all eigenvalues are negative definite. Okay. At least one eigenvalue 0, remaining all are positive semi-definite. At least one eigenvalues are 0, remaining negative is called negative semi-definite. Some are positive and some are negative eigenvalues indefinite. So once again I am repeating this one, nature. If all eigenvalues are positive, very simple, positive definite. For example, eigenvalues are 2, 3, 6. So 3 eigenvalues are positive, therefore the nature is what? Positive definite. Negative definite means if all eigenvalues are negative, is called the nature is negative definite. Let us say, for example, if you get suppose eigenvalues are -2, -3, -6. If all 3 eigenvalues are negative, therefore it is called nature is negative definite. For example, at least one eigenvalue 0, remaining all positive, then the nature is positive semi-definite. Positive semi-definite. For example, 0, 2, 3. 1, 0, remaining are positive. Therefore, positive semi-definite. In the same way, negative semi-definite means at least 1, 0 and remaining are negative. Let us say, for example, 0, -3, -6. At least we are having 1, 0 and remaining are negative. Therefore, it's negative semi-definite. What is indefinite? Very simple. Some are positive and some are negative. Is called indefinite. Let us take -2, 3, 6. Here, one eigenvalue having -2, negative, and remaining 2 are positive. Means some eigenvalues are negative, some eigenvalues are positive. Therefore, it is indefinite. So, from eigenvalues, we can conclude this all the rank, index, signature, and nature. Okay, but the main question we have that one, how to reduce the quadratic form to canonical form by using orthogonal transformation. So we have the procedure for that one, reduction of the quadratic form to canonical form, short form writing, by orthogonal transformation. So the question will come this like, reduce the quadratic form to canonical form. After that, find the rank, index, signature, and nature of the quadratic form. So how to reduce the quadratic form to canonical form by orthogonal transformation? Suppose we will give the quadratic form. So I will give the step-by-step procedure or working group. Step 1, what you have to do is, the step 1, write in the matrix form of the quadratic form. What you have to write? Write matrix A of the quadratic form. Then how to write the matrix A of the quadratic form? Write the matrix of the quadratic form means you have to express the given quadratic form in the matrix form. X transpose Ax. If the given quadratic form, if the moment we are expressing in the form of X transpose Ax, we will get A. Whatever the middle will get A, that is called the matrix of the quadratic form, and moreover, you always will get the symmetry. This is compulsory. Suppose even if you did not get, means you did somewhere else wrong. So you remember that one. So compulsory, the matrix of the quadratic form always symmetric. Okay. The step one is write the matrix A of the quadratic form. A must be symmetric. The step two, find eigenvalues. Find eigenvalue. Let us say, for example, A is a 3 by 3 matrix. Then we'll get the three eigenvalues. Let us say lambda 1, lambda 2, lambda 3. Okay. Then step 3, find eigenvectors. You know how to compute the eigenvectors for corresponding to each eigenvalue. For lambda 1 corresponding lambda 1, you can compute eigenvector, that is say x1. This is x2 and x3. That is x3. Then step 4. Up to this we are already familiar, finding eigenvalues and eigenvectors. Then after that, what we have to do is we have to construct the model matrix. Form model matrix. P is normalized eigenvectors as it's called. So what you have to do is divide by each vector by its norm. By its norm. Here generally, if the matrix is symmetric matrix, for example, there are two types of eigenvalues you will get. For example, let us say A, B, C. Eigenvalues are distinct case A. But irrespective of the nature of the eigenvalues, every symmetric matrix diagonalizable, whether eigenvalues are distinct, repeated and distinct, definitely. But here process is just slight difference in the process of diagonalization. Then find x. Then find x. Here x1 will get x1, x2, x3. Here also will get the three eigenvectors x1, x2, x3. But here they will automatically will become pairwise orthogonal. So we have the theorem on this one. What is the theorem? But here this is not happened in the case of the repeated eigenvalues. Whatever the eigenvectors will get, they are not pairwise orthogonal. This concept is called pairwise orthogonal. What does it mean by pairwise orthogonal? If the product of two vectors 0, they are called orthogonal. What is the pairwise? If you take any pair, they are orthogonal. We can say the pairwise orthogonal. If we have the three vectors, we will get the three pairs, we will get different pairs. So automatically, even without verifying, we can directly proceed. We have the theorem. The theorem says that eigenvectors, distinct eigenvalues of real symmetric matrix are pairwise orthogonal. Once again, I am repeating. Eigenvectors, distinct eigenvalues of real symmetric matrix are pairwise orthogonal. So I am writing directly. Means before constructing the model matrix, make sure that they are pairwise orthogonal or not. So this directly will become pairwise orthogonal if the eigenvalues are distinct. If eigenvalues are distinct, let us say A, B, C. For example, lambda 1 is equal to A, lambda 2 is equal to B, lambda C is equal to 3. Three different eigenvalues. Definitely whatever the eigenvectors will get, they automatically will become pairwise orthogonal. But what happens suppose if eigenvalues are not distinct, suppose repeated. In repeated case, we'll get the three eigenvectors, but they are not pairwise orthogonal. Since that, what you have to do is, now look at each pair, which pair fails the orthogonality. From that, remove that one of the vector, insert a new vector in such a way that is orthogonal to remaining two. So after making the pairwise orthogonal only, we have to construct the model matrix. We'll see in the problem that one. We'll do the two problems. One problem having different distinct eigenvalues will get directly get. But coming to second case, if eigenvalues are repeated, whatever the eigenvectors will get not pairwise orthogonal. But how to make it pairwise orthogonal, we'll see in the problem. Okay. So what we are doing is the step 4, construct model matrix. But make sure that before they are compulsory pairwise orthogonal. After verification of pairwise orthogonal only, you have to construct the model matrix P. Okay. So automatically will become the eigenvalues are distinct case, but in this case not pairwise orthogonal. How to make it pairwise orthogonal, we'll see in the problem. Now here, if the A is symmetric matrix, compulsory this model matrix will get the orthogonal. P is, since P is orthogonal, P is orthogonal. If P is orthogonal means P inverse is equal to P transpose. PP transpose is equal to I. What is the meaning of PP transpose is equal to I? Means P inverse is equal to P transpose. So this is the advantage of if the matrix is symmetric matrix. So whatever the matrix you will get, model matrix will get the orthogonal. But this is not happened in the case of non-symmetric matrix. So we have computed A inverse by this P inverse by using the formula adjoint P by det P. But here not required. Why? Because the matrix whatever we have, it is a symmetric matrix. If the matrix is symmetric, the model matrix compulsory will get the orthogonal. Once is orthogonal, what is the P inverse? The P inverse is the P transpose. Okay, is the P. Now, step 5. Let you will consider one transformation x is equal to Py. Hope you understand what is the x. X is what? It is a quadratic form. The variables in quadratic form, what are the given quadratic form? It is in variable x1, x2, xn. What is the P? Whatever the matrix, model matrix will get thrown. What is the y? We are converting to new variables. Let us say y1, y2, yn. So this is, and moreover P is what? Orthogonal. So be a orthogonal transformation. Be a short form writing is orthogonal transformation. Now step 6. Now what is the given quadratic form? The quadratic form is equal to what? X transpose X. X transpose X. Now just replace this in place of X. Py you write Py whole transpose A Py. Now this is we know this is AB whole transpose is equal to B transpose, A transpose, Y transpose, the P transpose, AP of Y. But here in step 5 I am continuing that after step 4 whatever it is. Now this matrix P diagonals the given matrix A. Means P inverse AP is equal to D. Therefore P transpose AP is equal to D. Better you can add it here, this step 4 only. After constructing the model matrix, this model matrix diagonalize the given symmetric matrix. Means P inverse AP is equal to D. What is the P inverse here? P inverse is equal to P transpose. Now P transpose AP is equal to D. What is the D? D is the diagonal matrix and diagonal means are the eigenvalues. So whatever the order you have taken for computing the eigenvector, thus order you have to write it here, preserve it. Okay. Now this is what P transpose AP is equal to what? D. Y transpose Dy. We know that from this. Since this is the P transpose AP is equal to diagonal matrix. Now let us take it, for example, A is the 3 by 3 matrix. Let us say new variable y is equal to y1, y2, y3. Now this is, let us say this is the A 0, 0, 0, B 0, 0, 0, C, D. Here what is the y? I am taking the y1, y2, this is y3. If you multiply, you will get 1 by 1 because it's a 3 by 3. This is 3 by 1. This is 1 by 3. If you multiply, what you will get? 1 by 1. That is nothing but so direct you will write it very simple in the way. Just scale sums will, but the coefficients are the A y1 square, B y2 square, C y3 square. So definitely we'll get only scale terms will get. The coefficients are nothing but the eigenvalues. What are the eigenvalues? You will get that one. So once you get the eigenvalues also, you can easily write it this one. But this is the way of computing this process. So which is what? Which is canonical form. Why it is canonical form? So in that we are having only, which is the canonical form, because we are having only scale terms, product terms are absent. This is called canonical form. We are reducing this canonical form by using which one? By using this one. What is this one? It is one of the transformation. Moreover, this transformation is orthogonal transformation. So by using this orthogonal transformation, the given quadratic form x transpose ax2 we reduces to y transpose dy. Y transpose dy also quadratic form, but it is a special type of quadratic form in that only sum of scales we have the product terms are absent. Such expression is called canonical form. And the coefficients of the scales are must be the eigenvalues you will get. Even if you know the eigenvalues also, even directly even without multiplying also you can directly write it. What you are trying the first one coefficient of y1 scale you write the first eigenvalue, y2 scale the second, like that. It is a canonical form. So after this canonical form you can find the rank, index, signature, nature. If this based on the coefficient nothing but the eigenvalues. If number of the number of terms in the canonical form is called rank, number of positive terms is called index, positive terms minus negative terms is called signature. If all eigenvalues are positive, we can say positive definite. If all eigenvalues are negative, we can say negative definite. 1 0, at least 1 0 remaining are positive, we can say positive semi-definite. At least 1 0 remaining all negative, we can say the nature is a negative semi-definite. Some eigenvalues are positive, some eigenvalues are negative, we can say that indefinite. So we'll do the problems in the next class. So today I'm ending the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.